All right, we're recording. Okay. Hey, you guys, I just finished drafting a video solution to week 3's quiz. I had never done this before. We'll see how it goes. If it's really bad, let me know and I can try to make improvements. I did provide a couple suggestions at the end as to how you might extend this problem or change it up a little bit to make it harder, to make it be more like something you might see on the midterm, to just challenge yourself a little bit. So if you found the solution I presented pretty easy, you can try solving some of the different problems that I suggest at the end. I'll try to provide those in the comment section of the video. Also, in the middle of solving the problem, I realized I didn't have the numbers of the masses or of the angle of the ramp or of the acceleration of M2 upward. So I had to look those up. And then I also took that time to type it into Wolfram Alpha. But yeah, I gave you the solution. So if you have any questions, let me know. Please let me know if this was good or bad, or if I shouldn't do it again, or if I should do it again. So like, comment, subscribe below. Anyway, love you guys. Good luck. Okay, you guys, today is October 6th. Let's outline the solution for Friday's quiz. You're given a ramp, some angle theta. You were told there's a mass here, M1, with another mass, M3 on it. There's a pulley attached to the ramp, frictionless mass pulley, with a string going over it. And then that string is supporting another pulley, which is itself supporting a mass, M2. You were told that M2 moves upward at a given acceleration, which tells you, of course, that M1 has to move down the ramp along with M3. And the question is, knowing M1, M2, M3, theta, and the acceleration of the second mass in the y direction, what is the coefficient of friction between mass 1 and 3? Okay, so let's see if we can find this information. The first thing we need to do is draw some free body diagrams. So let's start with a free body diagram of mass 1. So we'll just go in order. Mass 1, 2, 3. For mass 1, well, first, there's a weight force pulling it straight down. So that's M1G. Oh, I don't know. Let's erase all of that. Erase, 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 erase. Select the pen again. Okay. There's mass M1G pulling it straight down. Of course, there's a normal force from the ramp pointing upward. We'll just say F1R, normal force between mass 1 and the ramp. And then there's a normal force between masses 1 and 3, which I'll draw here. Now things are getting messy. Bear with me. There's a tension force pulling it up the ramp. And then there's a friction force between masses 1 and 3. Now, we don't know. We could think about it a little bit and probably figure out which way the friction force has to be oriented on mass 1. But for the sake of education, I guess, pedagogy, I'll not assume that I know. I won't try to figure out what the direction of that friction force is. I'm just going to pick one. So I don't know if this is right or wrong. I'm not even going to think about it. Turn my brain off for a second, and there's a force of friction going up. Great. So now this really messy diagram should have all of our forces on it. A normal force on mass 1 from the ramp, a normal force on mass 1 from mass 3, a weight force pulling it straight down, and then a tension force pulling it up, and I'm going to assume that the force of friction between masses 1 and 3 is directed up. If that's the wrong direction for the force of friction, there'll be a minus sign for the force of friction where there should be a plus sign, and that'll have told me that I should have put the arrow going down the ramp instead of up the ramp. So, okay. So that's the free body diagram for mass 1. Mass 2, let's put a little 1 here. Mass 2. Well, mass 2 is easy. It only has 2 tension forces pulling it up. A lot of people like to think there's 1 tension force pulling up on mass 2, but you can think about it like if the string, imagine the string is, so there's a cable attached from the pulley to mass 2, assume that the string is only wrapping around the pulley and isn't touching the structure supporting mass 2 at all. There's definitely a force upward on the pulley from the string on the right-hand side with tension T. And because the pulley itself is massless and frictionless, the exact same tension has to exist on the other side of the pulley. So there's actually two tension forces acting upwards on the pulley. That's what's pulling mass 2 up. So mass 2 feels 2T pulling up on it, while it feels its own weight force pulling down on it. Other than that, there's no forces acting on mass 2. So it actually looks like 2T up and M2G down. That's pretty simple. That's mass 2. Mass 3, that isn't so bad either. There's a friction force equal and opposite to the friction force that I assumed was acting on mass 1. So that's Newton's third law. For every action, there's an equal and opposite reaction. So there's a force of friction acting down on mass 3, assumedly. It might be the opposite, but it would be the opposite for mass 1 too, and it would just flip for both of them. And then there's a normal force. I'll say F1, 3. And then there's a weight force, M3G. Okay, this is all we should need to solve our problem. Let's do it. So let's set up our equations. At this point, I'm going to need some space. So I'm actually going to erase the diagram I drew, and I'm just going to keep the free body diagrams. This one looks terrible. And I'm going to write my equations over here. So, if you need the diagram, go back, pause the video, and write it down because it's going away. Goodbye. 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 Okay. Cool. So now all that's left is to write down our equations. If we have n equations and n unknowns, then we should have a solution to our problem, and we can walk away. See if we can find that. So first, I'll just work through the x and y coordinates of all the masses in order, and yeah, we'll see if we have enough. So for everything on the incline, it's going to be easiest to talk about the forces that act parallel and perpendicular to the incline, to treat it like a one-dimensional problem in the plane of the incline. For the pulley, it'll be easiest to talk about the pulley's motion in the vertical direction, because that's the only direction the pulley moves in. So if you ever have a system that only moves in one direction, like the masses on the incline or the mass attached to the pulley, use the coordinate system along the line of motion. There's no reason for me to assign a global coordinate system like x, y for everything, because this wouldn't be nice for the incline. It would only be nice for the pulley. And there's no reason for me to pick a coordinate system like, x, y, where this angle is the pulley angle, where this angle is the incline angle, because this wouldn't be nice for my pulley. My pulley only moves in the vertical direction. It doesn't move in the parallel or perpendicular direction to the incline. So the best coordinate system for me to use is actually two different coordinate systems. And that's not really a problem because, well, the acceleration of the pulley in the vertical direction directly corresponds to the acceleration of mass 1 down the incline. So we'll talk about that a little bit. We'll get there in a minute. So first, just writing all Newton's second law equations. So looking at the free body diagram for mass 1, if I look at the forces that act perpendicular to the incline, there's the normal forces between mass 1 and the incline itself, and mass 1 and mass 3. Also, there's a component of the weight force that acts perpendicular to the incline. And we know that's we know that's m1g cosine theta, where theta is the ramp angle. So I can write that the sum of forces in the perpendicular direction of the incline is F1r, the normal force between mass 1 and the ramp, minus F1 minus m1g cosine theta. That's 0. Why is it 0? Because mass 1 isn't moving into the incline or away from the incline. It's constrained to be on the surface of the incline, so it can't accelerate perpendicular to the incline. So I'm guaranteed that this is true. parallel to the incline. Now, I know that mass 2 is moving up, so mass 1 is moving down. I'm going to call down the positive direction so that my acceleration is positive in the downward direction. So I only have one force acting downward, and that's the parallel component of the weight force. That's m1g sine theta. I have two forces pulling me up, though. One is tension, and one might be the force of friction. So the force of friction might end up being negative. If that's the case, then I need to flip that arrow around, and the force of friction will actually be pulling m1 down the ramp along with its weight force, that component of the weight force along the ramp. Also, I'm denoting the acceleration of mass 1 in the parallel direction as a1 superscript parallel. So it's not an 11, it's not a double prime, it's just a parallel symbol. Okay. Then that's all my free body diagram equations for mass 1. These are all for mass 1. Now we'll do mass 2, x and y. Well, mass 2 only has one component of motion, only has the vertical component. So I know it's moving up. I'll call up positive. 2t minus m2g. That's m2a2 in the y direction. It has no acceleration in the x direction, and you were given this. So that's pretty cool. So we can actually solve for the tension now because we know what m2 is, we know what g is, and we know what a2y is. So we know what this is, we know what this is, and we know what 2 is. So t is just going to be m2g plus m2a2y divided by 2. Nice, we got it. And now we'll do the x and y equations for mass 3. So again, parallel perpendicular to the incline, there are only three forces I have to worry about. So there's a parallel and perpendicular component of the weight force and the friction and normal forces. So in terms of the perpendicular component, I would have F13 minus M3G cosine theta, and I would know that's 0 for similar reasons as before. It's not accelerating away from mass 1 or into mass 1. Mass 1 is supporting it, it's not pushing into mass 1, it's not accelerating away from mass 1, doesn't have rocket ships attached to it, so it's stuck on mass 1, so that has to be the case. And then there's two forces pulling it down. There's the force of friction, and then there's also m3g sine theta. And that's m3 a3 parallel. Okay, cool. And these forces are positive because I'm assuming that m3 is moving down the ramp. If that's not right, then a3 might be negative, and that's okay. It'll come out in the math at the end of the day. So now we need to figure out how many equations we have and how many unknowns we have. If we have as many equations as unknowns, we're fine. We're in a good spot. So we don't know any of the normal forces. So I'll use a different color now. I'll use red. Red. Cool. So we know this. We don't know that. We don't know this. We know m1, we know g, we know cosine theta. We don't know the tension. We don't know the force of friction. And we don't know a1 parallel. I don't want to double count here. We don't know the tension, but from equation 2, we already know that we don't know it, right? So I don't need to say that this is a new unknown. It's not a new unknown, but I also don't know this. I don't know F13, but I already accounted for that. I don't know the force of friction, but I already accounted for that. I don't know A3 parallel and everything else I know. So I have 1, 2, 3, 4, 5, 6 equations. Sorry, 6 unknowns and only 5 equations. So at this point, I've seen a lot of students try to figure out how to get the answer from here. But from a simple analysis, we can already realize that we don't have enough information to solve the problem. I have 5 equations and 6 unknowns. Unless I have one more constraint, we won't be able to solve the problem. And if we think about it a little bit, it's pretty easy to come up with what the last constraint is. Let me erase some stuff to give me some more space here. Of course, the last constraint has to be the one that tells me, go back to black here. The last constraint has to be the one that tells me just how mass 1, the mass on the incline, accelerates given mass 2, right? M1. If M2 goes up an amount delta x, that means that the string segment here got shorter an amount delta x, and also here by an amount delta x, such that both sides of the string pulled up mass 2 an amount delta x, which means that M1 went down an amount 2 delta x. So for every meter that M2 goes up, M1 goes down 2 meters, which means that if M2 has an acceleration of a2, M1 has an acceleration of twice that. If the distance is related by a factor of 2, then the speeds, the derivative of how much this changes as a function of time, will be related by a factor of 2, and so will the accelerations. So this is the last equation we need. The last equation we need is that 2a2y is equal to a1 parallel. What we need to solve for is the coefficient of friction between masses 1 and 3. Now, the force of friction, it looks like an M, let me erase it. The force of friction is calculated by taking the normal force between two objects, it's already here. The force of friction in general between two objects is given by taking some number, some coefficient, some measure of how rough the surface is, taking that number, some unitless quantity, times the normal force between two objects. So if you know how much grit there is on the surface, and you know how hard they're pressing on one another, you'll know just how strong the frictional force is between the two objects. Or said another way, the coefficient of friction between two objects is just the ratio of the force of friction that's generated to the normal force. So if I want the coefficient of friction between masses 1 and 3, all I have to do is solve for the force of friction here, here, and here, and then solve for the normal force here and here. Take the ratio of those two things, and I'm all done. So I'm going to erase my free body diagrams again to give myself some more space. Something cathartic about erasing stuff, even if it's digital. Oh, I can erase this too. What I'm going to do is first I'm going to solve for mu. Sorry, first I'm going to solve for the answer, and then you're done. It really looks like an M. It's a mu. It's not an M. I'm not going to fix it. Force of friction over normal force. Now the normal force is really the normal force between masses 1 and 3. So it's what I've been calling F13. But F13 is easily derivable from equation 4. Because mass 3 isn't moving perpendicular to the plane on mass 1, we know that the normal force between masses 1 and 3 is just m3g cosine theta. Great. Now we need to solve what the force of friction is. So the force of friction shows up in a couple different equations. I'm gonna try looking at the force of friction just by looking at the equation of motion for mass 1. And I'm going to do that instead of looking at this one with mass 3 because I want to take the information about mass 2 connected to mass 1 and use that to obtain information first. I want to start with what I know. I know m1, I know m2, I know the acceleration in the y direction for mass 2, and I know the acceleration of mass 1 now through this relationship. So I know the most stuff about masses 1 and 2. So since I know the most stuff about masses 1 and 2, I'm going to just kind of ignore this for now. If I end up needing it later, I'll use it. But I've already used 4, so it's done. The information is no longer needed. And I just want to use these other equations besides the ones related to M3 for now. Maybe I'll end up needing it. If so, I'll use it, but probably I won't. Let's see. Okay, So the force of friction, so using equation 2, is m1 a1 parallel plus t minus m1g sine theta. And I messed up, so all of that has a minus sign in front of it. So minus ff is m1 a1 parallel plus t minus m1g sine theta. Don't like the minus sign there, so I'm just going to write a new line. Sorry, you guys. m1g sine theta minus t minus m1 a1 parallel. Now we know m1, we know g, we know sine theta, and we know m1. We don't know t and a1 parallel yet until we realize that equation 3, we pretty much know everything except for t. We know 2, we know m2g, 2, m2g, we know m2 a2y because they gave us a2y. So we have the tension. We also have a1 parallel though. So I was saying that we don't know these two things, but we really do because equation 6 gives us a1 parallel. It's 2a2y, right? So I can write this as m1 g sine theta minus, and I'll consider this term first. I'm going to bring this term over first, and I'll write t at the end. m1, so I'll write 2m1 a2y I just want to make sure that's right. Yeah, cool. And then minus t. What's t? Well, t, if I look at this expression, oh, not this one, sorry. This one, equation 3. T is really m2a2y plus m2g divided by 2. So let me just write all that out. m2 times a2y plus g, all that divided by 2, right? That's my force of friction. And my answer is the force of friction, which is this. And this has everything I know. I know the acceleration in the y direction for mass 2. They gave it to me. I know g. Oop, damn, go away. I know g. I know m2. I know a2y. They gave it to me. I know m1. I know sine theta. I know g. I know m1. And I know m3. And I know g. And I know cosine theta. So at this point, we're done. We just got to plug in numbers. So at the end, it looks like m1 g sine theta minus 2m1 a2y minus m2 over 2 times a2y plus g all over m3g cosine theta. Okay, this is our answer. So let me erase more stuff. Now I don't remember what the numbers were. I should look at the problem statement again. Okay, you guys, I messed up a little bit. I forgot what the masses and accelerations were. The acceleration of mass 2 was. So I had to cut the video, and then I thought I would kind of summarize our result here in a little bit better, maybe a little bit cleaner form, a little bit more space, and then also show the free body diagrams for masses 1 and 3 because, well, that'll become clear shortly. So I'm actually going to plug all this in to Wolfram Alpha to get our final answer, and I will copy the URL that I pasted into, well, I'll copy the URL of the Wolfram Alpha result into the video description below so that you guys can see exactly how I plug stuff in to see, see that it all checks out and that it makes sense. But yeah, I'm going to take m1g sine theta minus 2m1a2y minus m2 over 2 times a2y plus g all over m3g cosine theta. So maybe I can minimize this a little bit and show you what it looks like in Wolfram Alpha. Let's expand this a bit. Cool. Go back here. I actually have it open from yesterday when I started making this video.
And you can see I have m1, maybe I can make this always on top. So I have m1 times g times the sine of theta minus 2m1 times a2y, and I put the units in everywhere, minus m2 over 2 times a2y plus g, and I wrapped all that in a giant set of parentheses, and then divided the whole thing by m3 times g times the cosine of theta. So you can see that I have m1 g sine theta, again, minus 2 m1 a2y minus m2 over 2 times a2y plus g, all divided by m3 g cosine theta. And I actually get minus 0.2634. Now, I know because I have the solution set that the answer is supposed to be 0.26, around there. So this looks right except for that minus sign. And let's think about why that minus sign might need to be a plus sign. If we look at this expression, the bottom's guaranteed to be positive. M3 is positive, G is positive, and theta is 30 degrees, and the cosine of 30 degrees is positive. So everything in the denominator is positive. So when you have the ratio of the numerator here and the denominator, the only way to get a negative result out of that fraction is if one of the two is negative. So it must be the case, since the denominator is positive, the numerator is negative. But I can think about this whole thing as being the numerator and realize that all of it's off by a minus sign. But what is the numerator? Well, the numerator is just the force due to friction. So that must be off by a sign. Let's think about why that might be the case. Originally, this was the free body diagram that I had for mass 1, and this was the free body diagram I had for mass 3. That minus sign tells me that the force of friction on mass 3 should actually be in the opposite direction, and the force of friction on mass 1 should be in the opposite direction, pointing down the ramp. Well, why would that be the case? Well, I think it's pretty easy to understand, actually, if we think about the problem. So, mass 1 here, it has a tension force pulling up on it. Mass 3 doesn't have that. If the tension force wasn't there, masses 1 and 3 would slide together. They'd both slide down the ramp with an acceleration of g sine theta. Remember that the acceleration of a mass down a ramp is completely independent of the mass. If you need to derive that, you should do it. Figure out what the net force in the parallel direction down the ramp is, and then figure out what the acceleration parallel to the ramp would be, and you'll find that it's independent of the mass. So if there was no tension, they would both accelerate at g sine theta. However, the inclusion of the tension force, the fact that the tension force is pulling up on mass 1 slows it down. But there is no tension force on mass 3. So mass 1 is going to move slower than it would otherwise. And mass 3 wants to move faster. That is, mass 3 wants to slide down relative to mass 1. So what's the friction force going to do to mass 3? Well, it's going to try to pull it back up onto mass 1. So if we look here at this expression, right, the force of friction is not going to push mass 3 down. It's actually going to pull mass 3 up to counteract what mass 3 wants to do freely. And similarly, the force of friction is not going to act up to pull mass 1 up the ramp. It's going to try to make mass 1 move down the ramp a little bit more. And so, since these objects aren't, so that's where the force of friction actually exists for the two objects, or that's how it acts for the two objects. It acts down on mass 1 and up on mass 3, and in a way that makes sense, right? Because this wants to accelerate down at g sine theta if there was no friction, but it can't. The friction force keeps it from moving down at g sine theta. And actually, if you calculate the accelerations of these two objects, you'll find that they're not the same. What does that mean? Well, it means that mass 3 is sliding relative to mass 1. I told my students that these objects would be accelerating together and that they'd be stuck to each other. I was mistaken. I didn't calculate the accelerations of mass 1 and 3 when I solved this problem originally. That was my mistake, so I apologize for that. If you calculate the accelerations of these two objects, you'll find out that mass 1 is moving relative to mass 3, and I'll let you figure out, how they're moving relative to one another. But how you can think about it is that, oh my gosh, I want to sneeze. How you can think about it is that the force of friction isn't big enough to keep them from moving relative to one another, or rather, the net force for mass 1 in the parallel direction of the ramp is such that it pulls mass 1 down at 8 meters per second squared, right? That's the acceleration of 1 parallel to the ramp. Why? Well, because the acceleration of 2 in the y direction is 4 meters per second squared. And we know that the acceleration of mass 1 is twice that of the acceleration of mass 2. So whatever the friction force is, it results in a net force acting on mass 1 such that it goes down the ramp at 8 meters per second squared. It has an acceleration of 8 meters per second squared. The question is the net force due to friction and tension and the parallel component of the weight force, are all those contributions perfect to keep mass 3's net force, which is just due to the weight force and the force due to friction, are they perfect to keep it accelerating at the same rate? If they are, then they're not moving relative to one another. If that combination of forces resulting in 8 meters per second squared is not perfect, then it's very likely that mass 3 will slide relative to mass 1. So I shouldn't have assumed that mass 1 wouldn't slide relative to mass 3. That's the reason the problem asks for the coefficient of kinetic friction, because they are sliding relative to one another. It's not immediately obvious, but if you work out the accelerations of mass 1 and 3, you'll find that it is the case. You could imagine if there was no friction, they would definitely slide relative to one another. And if you add a little bit of friction, if you add a little bit of coefficient of friction, then they will still keep sliding. And so this is just one of the cases where they do slide relative to one another. And I'll let you figure out how that happens. So now I can ask you the question, what is the coefficient of friction necessary in order to keep mass 1 stationary relative to mass 3? I can also ask you what would happen if mass 3 had a rope on it and it was coupled to mass 2 instead of mass 1. These are different variations of the problem that you could try to solve if this solution already makes sense to you. I think the one where you determine what the friction force is that keeps them from sliding relative to one another is an interesting one, and I think it's one worth trying to solve. In any event, this is the solution for the problem. If you guys have any questions, let me know. Yeah, I think I'm all done.